todos y bienvenidos. Hoy queremos celebrar con vosotros un acontecimiento muy especial para el canal AstroSpider-Love. Y es que hemos superado los 300 suscriptores y las 2000 visualizaciones. Por ello queremos compartir con vosotros un tema que para nosotros es muy especial. La misión OSIRIS-REx al asteroide Bennu. El asteroide Bennu orbita cerca de la Tierra y está compuesto por los materiales originales de la formación del Sistema Solar. Es por ello que fue elegido por la NASA para su misión OSIRIS-REx. En este vídeo, gracias a esta misión, conoceremos cómo se formó el Sistema Solar y acompañaremos a la misión OSIRIS-REx en todas sus vicisitudes y esfuerzos hasta alcanzar el asteroide Bennu y, lo más importante, obtener una muestra de su superficie. Y es que la misión no ha sido fácil, ha llevado muchos años de desarrollo y de viaje hasta alcanzar el asteroide. Una vez allí, los científicos se encontraron con una desagradable sorpresa, y es que la superficie de Bennu no era tan suave como ellos creían. La misión OSIRIS-REx mapeó el asteroide y encontró piedras de gran tamaño, algunas del tamaño de un campo de fútbol. Y es aquí donde esta misión se hace especial para nosotros, porque tuvimos una pequeña y modesta intervención en ella. Y es que gracias a los programas de ciencia ciudadana, cualquiera de nosotros puede formar parte de una misión tan emocionante como esta. Nosotros nos adscribimos al programa Bennu Mappers, en el cual se nos proporcionaron miles y miles y miles de imágenes de alta calidad y de alta resolución de la superficie del asteroide Bennu, y dedicamos muchísimas horas a marcar cada piedra, desde las más grandes hasta las más insignificantes, para que el equipo de científicos escogiera finalmente 4 lugares de aterrizaje y seleccionaran 2. Uno de ellos, el Nightingale, es el lugar de aterrizaje primario y otro de reserva. Por eso nos hace tanta ilusión esta misión. De hecho, ya se han comenzado las pruebas de toma de tierra de la misión OSIRIS-REx, que han sido un éxito, y en los próximos meses se tomará por fin la muestra de la superficie, que posteriormente vendrá de regreso a la Tierra para ser estudiada en profundidad y conocer mejor los secretos que esconde la formación del Sistema Solar. Esperamos que disfrutéis de este vídeo y, celebrando esos más de 300 suscriptores y 2000 visualizaciones, os animamos, si no lo habéis hecho ya, a que os suscribáis, a que nos acompañéis en este viaje a través de la ciencia, a que le deis a me gusta y a que activéis la campana para que os avise de futuros vídeos. Muchas gracias a todos por vuestro apoyo. Un afectuoso saludo.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
The OSIRIS-REx mission is an asteroid sample return mission, and the main goal is to collect 60 grams of pristine sample from the surface of the near-Earth asteroid Bennu. Bennu's rocky surface presented a challenge for the original LiDAR-based approach to the touch-and-go sample acquisition event. As an alternative, the project developed an onboard optical-based approach called natural feature tracking. NFT requires detailed three-dimensional maps of the surface of Bennu. In order to build those three-dimensional maps, we needed many, many images of particular patches of surface on Bennu itself.
And so all these surveys we've done throughout the mission have been at distances between several kilometers from the asteroid down to just a few hundred meters from the surface. And based on those different perspectives and what the shading of that terrain is, it's possible to build a 3D model. Very similar to how we have two eyes that allow us to have depth perception of what we see. NFT requires multiple features across the field of view to have a depth perception.
The original tag accuracy requirement was to touch the surface within a 50-meter diameter circle. Based on Bennu's rough surface, our actual performance has to be much better than that, at 10 meters or less. And even within that 10-meter area, there could be smaller localized hazards that may damage the spacecraft.
Right now, we are working on a flight software patch to help us avoid hazards as we come in for a sample event. When we do natural feature tracking, that is all autonomous on board the spacecraft, where we load the features or a catalog to the spacecraft, so we are telling it where we expect these features to be.
So as the spacecraft makes its progress down to taking the sample, we're recording images and then locating those landmarks to make sure we're on the right track. And if there's any issues with the trajectory or we see landmarks where we shouldn't, we know something's up and we can back away and wave off the attempt, try again.
In late 2018, as NASA's OSIRIS-REx spacecraft neared its target, Bennu, the asteroid grew in detail from a few tiny pixels to an incredibly high-resolution image. OSIRIS-REx confirmed the asteroid's basic shape, which was originally observed in 1999 by ground-based radar at Arecibo Observatory. What scientists didn't expect was just how rough and boulder-filled the asteroid would turn out to be. While it can be difficult to fully grasp Bennu's unfamiliar surface, it's helpful to understand the scale of what you're seeing here. In this image, the brightest boulder is the length of a horse, and the large boulder in this image is the width of a soccer field. Another challenge for the mission is the asteroid's small size and weak gravity. This means that OSIRIS-REx needs to fly daringly close to the surface in order to enter into orbit. With its orbital A phase, OSIRIS-REx successfully entered the closest ever orbit for a spacecraft, setting a Guinness World Record in the process. Then, 6 months later, it beat its own record during its orbital B phase and approached to within a few hundred meters of the rocky surface. Because OSIRIS-REx flew so closely over the surface during orbital B, the team was able to map the topography and shape of Bennu better than we have our own moon. In addition to mapping asteroid Bennu, OSIRIS-REx plans to collect and return a sample back to Earth. To do that, the spacecraft will carefully tag the surface of Bennu. The OSIRIS-REx team has selected 4 possible sample sites for the mission: Osprey, Kingfisher, Nightingale, and Sandpiper. The spacecraft has been closely imaging these sites from different angles to select the best touchdown spot for OSIRIS-REx. What was originally envisioned as a smooth and easy touchdown on Bennu's surface has become a complex endeavor to tag a small, crowded space on the asteroid, an area no larger than a few parking spots, by mid-2020. The OSIRIS-REx team has already pushed the boundaries of scientific exploration, going from ground-based radar images all the way to being a few hundred meters from the asteroid's surface, and is now mere months away from a sample collection attempt.
This is Bennu, a near-Earth asteroid, a remnant from the origins of the solar system and the target of NASA's OSIRIS-REx mission. When OSIRIS-REx arrived in December 2018, it brought Bennu into focus, confirming early radar images that suggested the asteroid was shaped like a spinning top. But the close-up images also brought a big surprise. Before OSIRIS-REx arrived, scientists had expected Bennu's surface to consist largely of fine-grained material, like a sandy beach. Sand heats up quickly during the day and cools off quickly at night. In contrast, solid objects like rocks and boulders heat up and cool down more slowly. Infrared telescope observations had shown that as Bennu rotates, its surface rapidly heats and cools, much like a sandy beach. But OSIRIS-REx was greeted by a rocky world littered with boulders, the size of cars, the size of houses, the size of football fields. This unexpected roughness confronted the mission with a major challenge. The main science goal of OSIRIS-REx is to briefly touch down on Bennu and grab a sample of fine-grained material for return to Earth. To protect the spacecraft, the original plan called for touchdown in a boulder-free zone with a diameter of at least 164 feet. But as it turns out, boulder-free sites of that size don't exist. Following arrival, mission planners began looking at safe zones that are just a few parking spaces wide, with enough loose material to provide a sample. In mid-2019, they identified 4 candidate sites and named them after birds that can be found in Egypt: osprey, kingfisher, nightingale, and sandpiper. Mission planners evaluated each site based on its safety to the spacecraft, the ease of getting to the site, the amount of sampleable material that it contains, and the science value of the material itself. After carefully evaluating these criteria, they chose Nightingale as the primary sample collection site and Osprey as the backup. Nightingale is located near Bennu's North Pole. It sits inside a small crater measuring 66 feet in diameter. Nightingale contains mostly fine-grained material and has multiple areas for sample collection. It is also the darkest of the candidate sites and has high color variation, suggesting a diverse mineralogy. Osprey is also located within a 66-foot wide crater just north of Bennu's equatorial bulge and may contain rock types from both the northern and southern hemispheres. Osprey has the strongest signal for carbon-rich materials of all 4 sites and contains a dark patch at its center that is of high scientific interest to the mission. Now that the primary and backup sites have been chosen, OSIRIS-REx is performing additional reconnaissance flights to prepare for the sample collection event. Later in 2020, the spacecraft will descend to Bennu's surface, briefly touch down, and collect up to 4.5 pounds of loose material. After collection, OSIRIS-REx will carefully stow the sample and make the long journey back to Earth. In late 2023, it will return the sample, delivering pristine material from the origins of the solar system that will be studied on Earth for decades to come.
Asteroid Bennu is a fascinating object. It records our solar system's earliest history, contains information about the origins of life, and has uncertainties in its orbit that leaves a small possibility of impacting Earth late in the 22nd century. These properties make Bennu the perfect target for NASA's OSIRIS-REx asteroid sample return mission.
It's a great adventure to explore an unknown world. We're going to reach out and touch it, and then we're going to bring treasure back to Earth for scientific analysis. To me, it doesn't get any more exciting than that.
There's a huge scientific payoff of delivering a sample of asteroid Bennu directly into the hands of scientists.
We want to understand the origin of the Earth, the origin of the Moon, the other terrestrial planets, but the earliest histories of those bodies is wiped out. The asteroids record the earliest stages of the solar system, so it really is a time capsule from the very dawn of the history of our solar system. My dream is that we find something that's unique, that's not represented in our meteorite collections, and is really organic, rich material on the surface of this asteroid that holds all kinds of scientific treasures about origin of life and organic molecular evolution in the solar system.
In addition to the planetary science, sending a spacecraft to asteroid Bennu will let us better understand the orbit of this near-Earth object. Bennu is 4,000 to 5,000 times more massive than the meteor that exploded above Chelyabinsk, Russia in 2013. And there's a small chance that Bennu could hit us late in the next century, depending on how its orbit evolves.
In order to accurately predict its future orbital evolution, we have to not only understand the force of gravity, but thermal forces on the asteroid can significantly alter its future path. So we're going to study not only the thermal emission coming off of Bennu, but we're also going to build up a global model to make sure we understand the theory that underlies this, and so that we can use it to accurately predict where Bennu is going to be in the future and apply it to other potentially hazardous asteroids to really help us understand the impact hazard.
OSIRIS-REx will launch in September 2016 and arrive at asteroid Bennu in 2018. Once the team is ready, they will use the touch-and-go sample acquisition mechanism, TAG-SAM, to grab a sample off the surface.
We have a unique design where we put this TAG-SAM device onto the surface of the asteroid, and then we blow down high-pressure nitrogen gas, kind of agitate the soil, and then basically scoop it up in a giant air filter. That whole process takes 5 seconds, so it's kind of get in, get the sample, and get out of there.
There's good reason to think this approach will work. One of the challenges of sampling an asteroid is navigating in a low-gravity environment. And with so little gravity, objects have a tendency to bounce.
Our design is to bounce off the surface of the asteroid. In fact, we've got a spring in the forearm of our TAG-SAM device, which is acting literally like a pogo stick to push us off the surface of the asteroid after we make that initial contact. So from everything that I've seen, trying to bounce off the surface of the asteroid is the easiest way to get that material.
Once OSIRIS-REx delivers the asteroid sample to Earth in 2023, it will have brought back the largest sample of an extraterrestrial body since the Apollo missions. And like the moon rocks from Apollo, this sample will be studied for decades to come with ever-increasing technology.
This is really a treasure of information about the history of our solar system, and will not only solve the scientific questions that we're asking today, but those that people will be asking for many generations into the future.
OSIRIS-REx is NASA's first asteroid sample return mission. So OSIRIS-REx will spend about 2 years journeying to asteroid Bennu. Once we get there, we'll spend a couple years surveying the surface of the asteroid to find the best place to get a sample from. And then we'll go ahead and return it to Earth and have that sample for scientists to study in perpetuity.
OSIRIS-REx is an amazing mission. It's the third mission in the New Frontiers line, a PI-led mission to go to asteroid Bennu, collect a sample, and bring it back to the Earth. Asteroid Bennu contains isotopes, minerals, and chemicals from the early solar system. And by studying these on Earth, we'll better understand the origin of the solar system, the origin of planets, perhaps even the origin of life.
Bennu was chosen as the target asteroid from the science team after evaluating 3 critical criteria, the first of which was accessibility. So Bennu is really optimal. It has an orbit of about 1.2 years, and it passes by Earth every 6 years. Second criteria was the size. We needed something large enough to where it wasn't rotating too fast. The smaller the body, typically the faster it rotates. We wanted something that we would be able to do close proximity operations with, all that detailed mapping we want to do of the surface. And we wanted something that was rotating at a speed that we could be able to match and then slowly lower ourselves to retrieve that sample. The third criteria was the composition. We wanted an asteroid that was pristine, that had a known geologic context, and that was carbon-rich. And Bennu really fit the mold for all 3 of those criteria, and that's why it's the destination asteroid.
OSIRIS-REx arrives at Bennu in August of 2018, and our mission profile is designed to get us ever closer to the surface of the asteroid to understand the nature of its surface. What we really want to know is, can we get the spacecraft down to the point where we want to get the sample? We call that deliverability. If we reach that point, will the spacecraft remain safe? meaning it can get away from the asteroid and still be functional, especially for returning a sample to the Earth. And then we also want to know if we touch down on that spot, will we get a sample? We call that the sampleability assessment. So those are the key parameters that drive our observation planning of Bennu, and we're going to spend about 10 months globally mapping the asteroid and then performing detailed site reconnaissance of specific locations where we think we want to get the sample.
25.
Status check.
Go Atlas.
Go Centaur.
Go OSIRIS-REx.
What I personally am most excited about for the OSIRIS-REx mission will be the first images that we get when approaching Bennu. So right now we have a sense of what Bennu looks like and what its shape is from ground-based assets like Arecibo and the Goldstone radars, but we won't know what the shape is completely, we won't have a perfect sense of it until we actually encounter the asteroid. I am going to be really excited when those images come back.
For me, getting that sample back to Earth is the most exciting part because we will have something that preserves material from over 4.5 billion years ago. Who doesn't want that? So sample return is really the most exciting part, I think, of this mission.
I've been working on OSIRIS and its precursor concepts since 2004. The launch is about the halfway point. So for me, launch is a major milestone, but not the most exciting part of the mission. The most exciting part is the stories that Bennu has to tell us that we haven't even thought of yet.
And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Fireworks look good.
On September 8th, 2016, in Cape Canaveral, Florida, OSIRIS-REx began its journey, NASA's most ambitious sample collection attempt since the Apollo program. After 2 years, including a gravity assist from Earth, the spacecraft arrived at its destination, asteroid Bennu. As OSIRIS-REx drew near, Bennu grew in detail from a few tiny pixels to a surprisingly rugged world, littered with giant boulders. The spacecraft has used its instrumentation to map the asteroid from all sides, mapping it in unprecedented detail. The mission team has been analyzing the data, scouring Bennu's surface to select the best sample site. Now, with just months to go before sample collection, the team has narrowed its target down to 4 potential sites.
OSIRIS-REx is a NASA mission to explore near-Earth asteroid Bennu, a remnant from the dawn of the solar system, and to return a sample of Bennu to Earth. On September 8, 2016, OSIRIS-REx began its journey to Bennu from Cape Canaveral, Florida, aboard an Atlas V rocket. It lifted off shortly before sunset, climbing eastward over the Atlantic Ocean to traverse the night side of Earth. 1 hour later, OSIRIS-REx separated from its Centaur upper stage rocket and drifted into space. It deployed its solar arrays to catch the rising sun and made a final pass over Australia before embarking on its outbound cruise to Bennu. After a year in orbit around the sun, OSIRIS-REx briefly returned to Earth in September 2017 for a gravity assist. The spacecraft passed within 18,000 kilometers of Antarctica, then turned its instrument deck toward home to capture images and spectra of the Earth and the Moon. The gravity assist bent the trajectory of OSIRIS-REx by 6 degrees, matching the orbital tilt of Bennu and sending the spacecraft on a path to catch its target. In August 2018, OSIRIS-REx began its approach phase. Its long-range camera captured the first visible light images of Bennu as a single pixel moving across a field of stars. Over the following months, Bennu grew from a pixel into a world, with OSIRIS-REx revealing its shape, rotation, and color for the first time. Now, after chasing its target for over 2 years, OSIRIS-REx is arriving at asteroid Bennu. On December 3rd, it will fire its thrusters to match Bennu's velocity and begin its preliminary survey. OSIRIS-REx will pass high above the equator and the poles, measuring Bennu's position and mass, and refining its size, shape, and spin. On New Year's Eve, OSIRIS-REx will venture close enough to Bennu to be captured into orbit by its minuscule gravity, making it the smallest world ever to be orbited by a spacecraft. In early 2019, OSIRIS-REx will break orbit to conduct a detailed survey of Bennu. First, it will carry out a mapping campaign called the Baseball Diamond. By observing Bennu at different latitudes and times of day, OSIRIS-REx will capture stereo images and identify large rocks on the surface that could pose a hazard later in the mission. In its second mapping campaign, OSIRIS-REx will observe Bennu from 7 different stations around its equator. At each station, it will take measurements from pole to pole using its mapping camera, laser altimeter, and 2 spectrometers. The combined data will provide a detailed look at Bennu's geologic features and its composition. This will improve landmark-based navigation and enable mission planners to begin looking for places to collect a sample. Following the detailed survey, OSIRIS-REx will once again enter orbit. At a radius of only 1 kilometer, Orbital B will serve as the mission's safe home orbit until sample collection. During this phase, OSIRIS-REx will globally map Bennu. It will fly in a polar orbit as the asteroid rotates beneath, enabling full coverage of the surface. Orbital B's precession, or wobble, will also be used to measure Bennu's gravity field, along with the non-gravitational forces that are slowly altering Bennu's trajectory. In mid-2019, OSIRIS-REx will begin its reconnaissance phase. It will break orbit and fly over 4 candidate sample sites at 225 meters, taking high-resolution images. Flying at such close proximity will reveal large pebbles that could pose a hazard during sample collection. Mission planners will use this information to select the 2 best sites for additional inspection. At a range of 525 meters, OSIRIS-REx will fly over the 2 final candidate sites, spectrally mapping the surface to reveal its chemical composition. This information will help mission planners determine the most valuable site for collecting the sample. Once the final site has been selected, OSIRIS-REx will begin its rehearsal phase. First, it will practice autonomous flight to a predetermined checkpoint, where it will start its descent during sample collection. Next, OSIRIS-REx will practice flying to the match point. The spacecraft will lower to within 30 meters of the surface to match Bennu's speed and rotation, a necessity for safely touching the asteroid. Finally, in mid-2020, OSIRIS-REx will be ready to collect a sample of Bennu. Before it descends to the surface, the spacecraft will deploy its touch-and-go sample acquisition mechanism, or TAG-SAM, a new technology invented for the mission. When it reaches the checkpoint, OSIRIS-REx will begin its final descent. It will pull back its solar arrays for safety and approach the surface at centimeters per second, the walking pace of an insect. As the TAG-SAM touches down, it will blow high-pressure nitrogen gas into the soil, stirring up loose material. A filter within the sample head will trap rocks and dirt while allowing the gas to escape to space. Once the sample is collected, OSIRIS-REx will fire its thrusters and back away from Bennu, retreating to a safe distance with its precious cargo. Following collection, OSIRIS-REx will verify the status of the sample using a camera called SAMCAM. This visual inspection will reveal whether any large debris is still attached to the sample head, which could pose a hazard during stowage. Next, OSIRIS-REx will verify the mass of the sample. It will fully extend its TAG-SAM arm and perform a spin maneuver, measuring the change in inertia to determine the sample's mass. If at least 60 grams have been collected and the sample head is clear of hazardous debris, mission planners will command the spacecraft to stow the sample. STOCAM will watch closely as the sample head enters the return capsule and is secured in place. OSIRIS-REx will then detach the TAG-SAM arm from the head, seal the sample return capsule, and prepare for its journey back to Earth. After departing from Bennu in early 2021, OSIRIS-REx will return to Earth in late 2023. 4 hours prior to arrival, the spacecraft will release the sample return capsule, then deflect away from Earth to its final orbit as its piece of Bennu comes home. The capsule will enter the atmosphere over the night side of Earth, streaking towards the central California coastline at over 12 kilometers per second. West of the Great Salt Lake, at an altitude of approximately 33 kilometers, the capsule will initiate its parachute sequence, stabilizing and slowing its descent. Upon landing in the Utah desert, the sample will be recovered, carefully removed from the capsule, and taken to the OSIRIS-REx curation facility at NASA's Johnson Space Center in Houston, Texas. This pristine material from the early solar system will be studied for decades to come, providing clues to the formation of the planets, to the evolution of Earth, and to the ingredients that were present at the origins of life.
The OSIRIS-REx spacecraft was launched with a clear mission: collect a sample from an asteroid called Bennu and send it back to Earth. But with the number of known asteroids in our solar system reaching into the hundreds of thousands, why was Bennu chosen? What made it the best target? The first set of selection criteria was proximity to Earth. The most accessible asteroids are located around 74 to 153 million miles away. And in that group, the most ideal targets are ones with an Earth-like circular orbit and a low degree of tilt due to spacecraft maneuverability. At the time of selection in 2008, that brought the number of known near-Earth objects down from 7,000 to 192. From there, the size of the asteroid became a factor. Bigger meant better in this case, because asteroids with smaller diameters rotate faster, and material on their surface are more easily ejected. Not ideal conditions for safely grabbing a sample. So, mission scientists wanted the target to have a diameter larger than 200 meters. That brought the candidates down from 192 to 26. The chemical composition of the asteroid was the next factor, because we want our return sample to help us learn more about the history of our solar system and life on Earth. That dropped our target list to 12 asteroids with a known composition. And from there, only 5 of those were ideal for sampling because they are known from Earth observations to be carbon-rich. This matters because a carbon-rich asteroid may contain organic molecules, volatiles, and amino acids that may have been the precursors to life on Earth. So, now it's decision time. Of these 5 contenders, why Bennu? Quite simply, it's because there was more information about it available to scientists. It was the only object of the 5 that had been observed with radar. This provided not just an accurate measurement of its size, dimensions, and shape, but also suggested it has a smooth surface with an ample amount of material to sample, and few large boulders to get in the way. We didn't have this level of detail with the others, which put the ability to safely get a surface sample in doubt. Sorry, fellas. The material we gather from asteroid Bennu will help generations about the past. Studying Bennu can help us plan for the future. Everything from space travel to utilizing natural resources and better understanding the risks of asteroids. And this is why we chose Bennu.
NASA's OSIRIS-REx spacecraft is heading to asteroid Bennu and back. The OSIRIS-REx mission goal is to study near-Earth asteroid Bennu and return a sample to Earth. OSIRIS-REx's launch window opened September 8, 2016 from Space Launch Complex 41 at Cape Canaveral, Florida. And the OSIRIS-REx spacecraft releases from the Centaur upper stage. Angled toward the Sun, the spacecraft deploys its solar arrays. Now traveling over 25,000 miles per hour, OSIRIS-REx escapes Earth's gravity and begins its cruise toward asteroid Bennu. After 23 months, the spacecraft arrives at asteroid Bennu in August 2018. With its suite of observational instruments, OSIRIS-REx orbits the asteroid, studying its characteristics and mapping its surface. After 4 phases of survey observations, OSIRIS-REx begins preparations to collect the sample. In July 2020, after months of rehearsals and study, the spacecraft approaches for sample collection. It slowly descends to Bennu's surface at less than a quarter mile per hour. With an outstretched arm, OSIRIS-REx briefly touches the surface. The touch-and-go sample acquisition mechanism, TAGSAM, blows high-pressure nitrogen gas into the surface rocks and dust, sending loose asteroid material up into the TAGSAM head. OSIRIS-REx backs away from Bennu and stows the sample in a capsule for its journey to Earth. in March 2021, the window opens for OSIRIS-REx to depart Bennu. The spacecraft returns to Earth September 24, 2023, and jettisons the sample return capsule. The spacecraft leaves Earth, and the return capsule enters the Earth's atmosphere at over 27,000 miles per hour, protected by a heat shield. A couple miles above the surface, a parachute deploys. And the capsule lands softly in the Utah desert. Bennu's secrets can now be investigated for decades to come.